Thank you, everybody, for attending my talk. So I will try to do my best not to disappoint you. Sorry, could you just regulate a little bit because it resonates? Can you regulate it? Fine, thank you. And what I will do, I will share with you some of our recent results, focus on the modeling of sprays. But my main focus will be not on modeling of particular phenomena, but rather sharing with you my philosophy of modeling, or my general approach to modeling, which can have a much wider range of applications compared with what I'm going to show to you today. And now I will try to, so this is the plan of my presentation. I will start with the background, and then I will focus on three specific problems. First is modeling of drying droplets, then modeling of suspended droplets, then microexplosions. And then, if time permitting, then I will give you a very brief overview of other developments in the field. And I will start with the background. So this is an overview of activities of our laboratory. So we are primarily interested in study of internal combustion engines. So that means that we don't develop engines themselves, but we develop tools which allow engineers to develop most efficient and least pollutant engines. So as you can see, there is a wide range of activities going on, and I'm involved mainly in the activity which is related to sprays. And this is something that is encircled here. So that means that my focus will be primarily on automotive sprays. But the tools which was developed for automotive sprays are very similar and sometimes identical to the tools which are applicable to modeling other classes of sprays. For example, sprays in turbines, sprays in pharmaceutical applications, sprays in environment, and I could continue this list. And as you know, it is my first presentation. It is not my first presentation here. And last year, I gave a lecture with a rather similar title. So the beginning was exactly the same as for the current lecture, but the second part was a little bit different. And this was the plan of my last year lecture. So I started with the background and then considered Lagrangian approach and full Lagrangian approach, spherical, non-spherical droplets, and then heating and evaporation and ignition. And I assume that many of you attended my last year lecture, and I try to do my best to avoid overlap between what was covered last year and what I'm going to cover today, except perhaps the background. The background will be rather similar as as to the background, what we're interested primarily in droplets, because spray consists of droplets. And in contrast to most of models which are published in the literature and available in commercial CFD codes, we take into account the temperature gradient inside the droplets. And also, in contrast to most of research in this area, we considered the effect of thermal radiation as a volumetric effect. So that means that we take into account the volumetric heating of droplets by thermal radiation, and this is taken into account by this term. And also we apply this equation, which assumes spherical symmetry of droplets, not only to the stationary droplets, but also to the moving droplets. And this is done by introducing the so-called effective thermal conductivity. And this effective thermal conductivity is linked with the liquid thermal conductivity by this simple formula. I am not going to go any further here because that is something that I discussed many times in the previous presentations. And I will move to another equation which is widely used in our modeling. This is the equation for species diffusion. So the droplets which we're dealing with are multi-component. So there is no automotive fuel which consists of a single component. And this leads us to the problem of species diffusion inside the droplet. This species diffusion is described by the species diffusion equation. And the species diffusion equation, again, is presented for spherical symmetrical case, but it can be applied for the case of moving droplets by introducing the so-called effective diffusivity model, in which the effective diffusivity of species is linked with the liquid diffusivity by this simple equation. And then the problem with the applications of this equation is that, yes, and all these models were implemented into computation fluid dynamics codes, and this is one of our recent publications on this subject. And the problem is that when we deal with automotive fuels, the number of components appears to be significant. It could exceed 100 components. And in this case, solving equations for each component would be a bit time-consuming. And to deal with this sort of problem, and this is the composition of realistic diesel fuel, we developed the so-called multi-dimensional quasi-discrete model, in which the groups of components were replaced by the so-called quasi-components. Quasi-components are not the real components which you can touch, which exists, but at the same time there are some sort of a ghost components. But these ghost components appears to bring some sort of a real benefits of to modeling. This is something that I covered more or less last year. And I'm not going to consider it in any further details here. And now I'm going to move to specific problems, and I will start with droplet drying. So droplet drying is a classical problem in many applications. For example, in pharmacy, when we produce a powder with a drug, then we need to dissolve, a certain drug first, and then dry the spray, and as a result, you got the powder like this, the powder like this. Then the problem is how to model this drying process. You have a lot of particles, which are moving inside the droplets, and then the surface of the droplets evaporates. So you can try to trace, for example, trajectories of individual particles, but you can do this, but this approach would be rather complex. Instead, we suggested a different approach. So these particles can be, these ensemble of particles can be treated as non-evaporating fluids. Non-evaporating fluids, and as a result, the mixture of particles and water, distilled water, can be considered as a mixture of two fluids, two liquids, one evaporating liquid and one non-evaporating liquid. And here we have the formulation of the problem. We have a Chisasan which is dissolved in water, and the mass fraction of Chizzy-san is 0.4%, and the mass fraction of water is 99.6%. And so these are initial conditions for ambient air for Chizzy-san, and these are the properties of Chizzy-san. And then, once we made this assumption, then we are on the track on the model which was developed for completely different problems. The model which was developed for automotive fuels. This has nothing to do with automotive fuels. And we use the same equation for species diffusion, which was shown in the background. And then this equation can be solved numerically, and this is something that was done in several papers. But in our case, it was solved analytically. And this is the analytical solution to this equation. And I'm not going to show the details because it would be a bit irrelevant for the main message of my presentation. So these are, at the boundary, we assume that liquid is, the water is the only evaporating substance, and Chizzy-san is not evaporating at all. And then we use the so-called Raoult law at the surface for the evaporating water. And then, once we have solved this problem, then we can get the time evolution of droplet radius and the time evolution of mass fraction of water and mass fraction of Chizzy-san. And we cannot really validate rigorously all these plots, which are shown here. But what we can validate is the typical time of evaporation of the droplets. And typical time of the evaporation of the droplets is about 0.12 seconds, is compatible with the experimental observations. And these results were published last year in our paper, prepared together with a colleague from Department of Pharmacy at our university, and also the colleagues from Kazan University in Russia, not far from here. And now I'm going to move to another topic, which focuses on suspended droplets. And this is the motivation of this work. That is our colleagues at Tomsk University. It is a little bit too further on to Siberia. Performed a number of experiments in which the droplets were suspended on a metal rod. And then the temperature of the hold of the rod increases with time, as it is shown here, depending on the temperature of the ambient air. Now we had an observation, the technique, the experimental technique which they could use, allowed them to estimate the temperature distribution inside the droplet. And here you see some typical profiles at various cross-sections and at various time instants. And the same distribution is presented on these plots, where we have the actual plots of the temperature inside the droplets versus the distance from the droplet center, And now the problem is how to model this phenomenon, because this phenomenon appears to be quite complex. You have a complex connection between the droplets and the rod. And it looks as if we are almost bound to perform a three-dimensional modeling of the phenomenon, which would be very time-consuming. And I would question the need of these sort of developments. So what we did, we tried to solve this problem, but using a different approach, using a simple approach. So what we did, we based our analysis on the heat transfer equation inside the droplet, including the radiation term. This radiation term takes into account the volumetric, in the general case, it takes into account the volumetric absorption of thermal radiation inside the droplet. But at the same time, you need to stretch your imagination that the same equation could be applied to any other means of volumetric heating of the droplets, not necessarily thermal radiation. And these other means could be heating via the transfer of heat through the rod. And then once we have made this assumption, then our task would be to calculate the amount of heat which is transferred through the rod to the droplet. And then once we calculated this amount of heat transferred through the rod to the droplet, then we would be able to calculate the value of the source term. So this is the underlying philosophy. All the rest is just a bit of calculations. So what we did, we used the analytical solution to this equation, including the source term. The nature of the source term at this stage is not specified. We will specify it a little bit later. And the analytical solution is presented here. This is the equation, and this is the analytical solution. And here, this term takes into account the effect of thermal radiation. But for me, at the moment, is not necessarily thermal radiation. It is whatever means of internal heating of the droplet. And now we are going to estimate, this sort of level of heating of the droplet, but not by the thermal radiation, but by means of transfer of heat by conduction through the rod. And then we solve a very, very simple problem. Very simple problem. We have the cross-sectional area of the contact between droplet and the rod. We have the temperature at the center of the droplet. We have the temperature of support, or the temperature of the rod. We have average radius of the rod. And then we have the thermal conductivity of water. It's a very simple formula. You can find it in a manual for undergraduate students. And then we can make another assumption, is that this heat is, strictly speaking, it will be distributed inside the droplet. But inside the droplet, you have a lot of convective processes. If not the forced convection, then it could be a natural convection. And these convective processes lead to the mixing of various layers inside the droplet. And then when this mixing takes place, then we can replace this heat transfer to the droplet to heat supplies to the unit volume of the droplet. So we assume that this heat supply to the droplet is uniformly distributed inside the droplet. It is uniformly distributed inside the droplet. And then once we have obtained this heat uniformly distributed inside the droplet, then mathematically this heat can be replaced by this source term in a heat conduction equation. The source term in heat conduction equation. So as you can see, we use the equation which was originally designed to take into account the effect of thermal radiation on heating of droplets, but applied to the case of the droplet, which is heated via the rod. And then once we have done this, then we can get the plots of temperature versus distance from the center of the droplet, and we have with a reasonable deviation between the results, reasonable agreement with experimental data. And these results were published in our joint paper with the colleagues from Tomsk University, and it was published last year. And now we are going to move to the last problem, the last topic of the presentation, which is focused on microexplosions. So perhaps not many of you know that to improve the performance of internal combustion engines, people tend to add water into the fuel, water in diesel fuel. It looks bizarre, but at the same time, it produces a very interesting effect, that water dissolved in fuel forms some sort of subdroplets inside the fuel droplets. Now, the boiling temperature of water is well below the boiling temperature of most components of diesel fuel. And as a result, when the diesel fuel with water subdroplets is injected into the hot chamber, in a diesel engine chamber, then they are heated, and when the droplet temperature, when subdroplet temperature reaches the boiling point of water, then they explode. And when they explode, then a big fuel droplet turns into a number of very small subdroplets, very small aerosols, which evaporate very quickly, and this improves the performance of the engine. So this is the underlying philosophy behind the microexplosions. There are a number of other reasons for this, but this is something that I'm not going to discuss today. And this is a typical video of what is going on during microexplosions. And then we can have a closer look at a sequence of photographs, which can give you a bit of a clearer view of what is going on with the microexplosions. As you can see here, you can see some sort of a small subdroplets in the fuel droplet, and then these subdroplets start increasing, and eventually everything explodes. Everything explodes here. And now, this is the reproduction. This is the reproduction of the pictures which are shown by my colleagues from the group and the group in the University of Malaysia. And please note that seconds here need to be replaced by milliseconds. Now the problem is how to model this phenomena. And the interest in modeling this phenomena is, was quite substantial. And a number of groups, including the group in our university, in the University of Brunel, together with a research fellow from Japan, they developed a very sophisticated model based on direct numerical simulation of all the processes inside the droplet. They try to trace all these interfaces between the water and the fuel and air, and produced quite impressive results. Here you can see quite impressive results. and which show the evolution, the detailed evolution of these water subdroplets inside the fuel droplet. And clearly, you know, it is, so everybody, including me, were quite impressed when we saw these pictures. But the problem is that these pictures were obtained for very specific initial and boundary conditions. When you change these initial and boundary conditions even slightly, then the whole picture will be different. And this brings us to a point where we need to decide how exactly we are going to use these sort of pictures for engineering applications. For the engineering applications, we don't really need to know all these, each and every of these details. What we need to know is that where the explosion will take place and when exactly, what is the typical time delay between the injection of the spray and the time of microexplosion. So, and this led us to not to try to compete with this group and try to develop some sort of a more sophisticated direct numerical simulation model, but try to approach to the problem from a completely different perspective. So what we did, we developed a very simple model. So we considered that a water subdroplet of a radius of RW is located in the center of a big fuel droplet of radius RD. Then the temperature at the interface between water and fuel is TW, and the temperature at the surface of the fuel droplet is TS. And then we return to the same heat conduction equation inside the droplet. In the general case, we use this source term due to thermal radiation, but eventually, you know, we are not going to we're going to assume that this term is equal to 0, okay? And then in this equation, what we did, we took into account the existence of two layers, that is the layer of water and the layer of fuel. And also in the general case, we took into account the difference between the distribution of temperature in the water and temperature in the fuel. And also we use a set of boundary conditions at the interface between water and fuel, and also a typical boundary condition at the surface of the droplet. And then these boundary conditions at the surface of the droplet were simplified. So at this stage, when we wanted to use to make some sort of first steps, some sort of preliminary results in the modeling, then we eventually replace these general Robin boundary condition by a simple Dirichlet boundary condition. We managed to justify, you know, this sort of simplification. It's a bit of a crude assumption, but at the same time, this assumption is workable. And then we made a long list of assumptions. One of the assumptions, the first assumption was that we assume that the temperature at the surface of the droplet is fixed, and it doesn't change with time. Then we assume that effects of droplet heating and effect of swelling and evaporation can be ignored. And obviously, you know, during the time of microexplosion, that these swelling and evaporation are relatively small. And then we can assume that initially the distribution of temperature inside the droplet doesn't depend on the distance from the center of the droplet. And then the effect of the source term is taken into account initially, but eventually it was ignored. And once we made this assumption, then the analytical solution to this equation turns out to be particularly simple. So it is shown here, and this is the meaning of the term. and the meaning of other terms is presented here. So it is, there are a lot of symbols, but at the same time, the structure of the solution is not particularly complex. And then, once we reached the solution, then we applied it to a particular experiment, which was performed in a group at the University of Petronas in Malaysia. And these are input parameters for the droplets, which were supplied by my colleagues working at that university. And as a result, using this solution, we were able to describe the heating of the droplet with time. So, for example, initially we had a jump. We had a jump in temperature between the droplet and the ambient air, and then we have a gradual spread of heat inside the droplet. And this leads to the gradual increase of temperature at the interface between the water and the fuel. And eventually, at some stage, that is time instant 5, we have this temperature at the interface between water and fuel reaches the water boiling point, And we assume that at this stage we have microexplosion. Strictly speaking, it will be puffing, which leads to microexplosions. And once we have prepared a number of curves like this, we were able to plot the time to puffing or time to microexplosion for different values of surface temperature and different values of the initial droplet temperature on this graph. This is the initial droplet diameter, and these are the values of time to puffing, which is assumed to be equal to the time to microexplosion, and as a function of the initial droplet diameter. And on this plot, on the same plot, we put the experimental results. And clearly, we couldn't get, one-to-one correspondence between experimental and modeling results, but at the same time, we have a correct order of magnitude. And also, we were able to show that our model at least predicts the minimal value of the delay time. And this minimal value of time to puffing is due to the fact that we didn't take into account the initial heating of the droplet, but we assume that the temperature of the droplet immediately reaches almost the boiling point. And then these results were published in the paper in the International Journal of Heat and Mass Transfer early this year. And these include our co-authors from the University of Petronas. And then I will just summarize briefly some other developments in the field. So one of the directions on which we are working very closely with this university is focus on the development of new mathematical tools for modeling of spray ignition and combustion. So the expertise in this field lies actually not in our group, but mainly in the group of Professor Sobolev, and this is our most recent paper on this subject, which is published in the Journal of Engineering Mathematics early this year. And then, another direction of research is focused on modeling of blended fuel heating and evaporation using previously developed theoretical tools. And this paper was prepared by my former research students and then research student of my former research student. And we just build it up, and we build it up this model on our previous model, and it is essentially focused on the refinement of the previously developed model. And then another direction was of research is focused on further development of the full Lagrangian approach, and which was described the last year, and we added new models, new submodels into these approach, and then it was implemented into computational fluid dynamics codes fluent. Then we try to generalize our previously developed model when taking into account the activity coefficient during the evaporation process. And then much of our research is focused on the modeling of vortex rings inside the engines. That is something that we regularly observe. And we try to develop relatively simple models of the phenomena. And this work is mainly performed in collaboration with our colleagues from Rouen University and also from Estonia. And our future plans is to incorporate multi-phase flows into this model. And I would like to thank EPSRC and other groups for supporting of our research. And thank you very much for your attention. And I think that I kept well in time.
That's your time, so thanks for keeping your time. I left 5 minutes for questions.
Yep.
Any questions? So I understand, yeah, it was clear presentation.
Yeah, there is.
Yeah, but even for computer scientists. But we have one question, and if anyone else wish, please, we have marked microphones. If the next question we have, please pick up one of those microphones. Go ahead.
The question is about droplet evaporation speed.
Sorry?
Question about droplet evaporation speed.
Yes.
Droplet evaporation speed depends not only on diffusion of components inside the droplets, but even of convection and diffusion of components outside the droplets in the outer gases. How did you solve this problem?
Okay. We didn't solve the problem, but we used a solution developed by other groups. So I didn't want to deliver a lecture, a comprehensive modeling of droplet heating and evaporation, considering both effects in the liquid phase and in the gas phase. So this would need a separate lecture. And what I did, I focused on the results which were specifically obtained in our group. So you're absolutely right that there are processes in the gas phase which we took into account in the modeling. I wouldn't be able to give you a very short answer to this, but my short answer is that we use a previously developed model and there is no development from our side here.
Okay,
Have I answered my question?
Yes.
Okay.